Hi, IB physics students. It's Mr. Hofstad here, and I'm coming at you with our new unit, topic 5, all about electricity and electric circuits. And it's going to be a little bit weird, especially this lesson, because it's built on stuff that you haven't learned yet from Physics 30, which is unfortunate, but that's just the way that the IB program is laid out here. So we'll kind of just do brief introductions, but don't stress too much. You will learn a lot more background to this in grade 12 next year in your Physics 30 course. If you want, I can attach some notes from that course for you to take a look at and get some background knowledge if you're feeling totally lost and confused. But I'll try my best to give you something to work with here. So these are what you should already know about electric forces and electric fields. I am aware that you haven't learned about these yet though, so we'll try our best to work with it. Try to think about it analogously to gravity, right? We have gravitational force, which we covered in Physics 20, and we have gravitational fields. Electric forces and fields are very, very similar, but instead of having two objects with mass being near each other, putting a gravitational force on one another, we now have two electrically charged objects nearby, right? And anything that has mass produces a gravitational field. Now everything that has an electric charge produces an electric field. So we have two types of charges. We've got our negative and our positive, where a negative charge has an excess of electrons and a positive charge doesn't. It has fewer electrons than it does protons, right? It's missing some electrons. And these guys are going to be attracted to each other, right? Opposites attract when we're talking about electricity or magnetism, right? So they both want to become neutrally charged, so they're going to be attracted with this electric force, and they're going to this negative charge, negative electrically charged object is going to give electrons to this positive one, which is missing those electrons, and everything in the universe just wants to be neutral. We want to have a nice even number of electrons. So kind of similar to ionic compounds, right? We're just swapping electrons around trying to become neutral. Okay, our kind of starting point for Physics 30 is static charges. I'll just briefly go through it with you. When you rub two things together, classic example would be rubbing a balloon onto your hair, you're producing static electricity. And this will work best with an insulator, right? Something like glass or styrofoam or, a balloon. Because the charges that you're building up through friction, so when you're rubbing two things together, you're getting electrons actually jumping from, let's say I'm rubbing this with this rod here in this picture with a wool cloth. I'm going to have electrons jumping from the wool into the glass. Actually, I think it's the other way around. It depends which object has a stronger pull on their electrons. So depending on where they fall on an electrostatic series, which you'll cover next year, right, we're going to get electrons either jumping right away or towards this glass rod and leaving it as either a negatively charged rod or a positively charged rod. And if it's an insulator, right, that negative or positive charge can just exist there without immediately jumping to another object near it. If it was a conductor, right, that those electrons would be more free to move around and they'd escape more easily. So with insulators, we can build up this charge and maintain it. And when you're bringing something with a net negative or positive static charge near other objects, right, whether they're neutral or oppositely charged, they're going to be attracted, right? And if you've watched the other YouTube videos, right, if we have like charges, we know they're going to repel. So static charge is all just about producing a charge by friction, so rubbing two objects together. You're giving energy to the electrons within that object's atoms, and those electrons are going to become excited and go on a little journey into the unknown, take the hop away from their parent atom and join up with another atom or object, leaving a negative or positive charge. So we also have things called conductors. So insulators don't really exchange charge that much, which is why they work well for static electricity. Conductors are really good at conducting electricity. That's where we get that word from. They are good at conducting electricity because they have many free electrons. So they've got lots of electrons within their lattice structure, right? Usually we're thinking about copper as a great conductor. So I'll use that kind of as an example here. In a copper wire, there's a whole bunch of free electrons. They're not really bound to, they have no loyalty to any one specific copper atom. Instead, they're free to do as they please, walk around, take a little trip across this copper wire, going through, around and about other atoms. Those atoms that are able to do that are called free electrons. Sorry, those electrons are known as free electrons when they don't have any loyalty or association to one particular atom. And when we have these free electrons, right, it's easy for them to move through a circuit. All right, so pay attention whenever you see something drawn like this. It's our cell, our electric cell, or our battery. And where you have the longer lines is our positive, where we have the smaller is the negative. And here these red dots are the electrons that are actually flowing, right? So negative electrons are going to repel from this negative side, this part of the cell that is negatively charged, and they're going to be attracted to the positive, right? Because the negative repels the like charges, the positive attracts the opposite charge. All right, charge cannot be created or destroyed. Just like energy, the charge needs to be conserved. It needs to be constant, right? This negative charge can't just disappear. When these two guys join up and form a neutral charge, right, still the net charge stays the same. Let's say this is plus one electron, which leaves it with a -1 charge. And this is missing one electron, right, leaving it at a +1 charge. When they join up, right, they still have this net charge of 0, right, because we're not able to create or destroy charge. Right, and this idea of an isolated system is also important, right? When we're looking at an isolated system, we're just looking at one specific spot in the universe, right? You can make your system as small as, I don't know, one atom, or as big as a solar system, or even the entire universe. Whatever system you're looking at, as long as it's isolated, meaning there's no external energy or forces or anything coming in or out of it, everything is kind of stuck within that imaginary bubble around it. The charge within that isolated system or that imaginary bubble will remain constant. Right, these positive guys are attracted to the negative, right? They're positive that they are. This is just that idea that they want to become nice and neutral. They don't like existing in this lonely negative or positive state. They want to form a nice neutral couple. Opposites attract. Charges attract, right? And if we have two like charges, they're going to go away, repel. All right, this is a big focus of Physics 30. We have this fancy British guy, Coulomb, in 1785, who was playing around with some pendulums and electrically charged spheres, and he created what we know as Coulomb's law, which will be on your formula sheets always, and it's stating that the electric force, Fe, is equal to some constant, which he got named after himself because he came up with it. We write it as K. We call it Coulomb's constant. It's equal. You don't really have to know this now. It'll always be given to you. But Coulomb's constant is equal to 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Right? So this constant is always true when you're finding, or is always used when you're finding an electric charge. And you're multiplying it by two charges, Q1 and Q2. Right? If they're both positive, this is going to be a repelled electric force. If they're positive and negative, opposite charges, this is going to be an electric force that is attractive. And we're dividing this Coulomb's constant, both charges multiplied together, by the radius or the distance between the two charges squared. Right? So he came up with this equation by running a bunch of experiments where he determined that the electric force is directly proportional to the charge, and it has an inverse squared relationship with the distance. So bringing these two charges twice as far apart would reduce the electric force 4 times, right? Just working with proportionality there. So he was looking at, the difference in distance between two charges and the difference in charges, all affecting this electric force. This will be covered quite thoroughly in Physics 30. For now, I don't know. Just keep in mind that we can calculate electric force when we know two charges and the distance between them. All right, something brand new, kind of confusing. We got electric field patterns. So an electric field we can draw with these field lines, we call them. They're arrows, and you're always going to draw them so that if you placed a positive charge, right, we use positive charges as our kind of test charge to decide what direction to draw these lines. If we put a positive charge here, right, it's obviously going to be directed, right, away. They're going to repel. So when we're drawing electric field lines, right, we're showing where if we placed another positive charge in this case, right, we'll always use a positive charge, but it could be negative, right, then it would go towards it, would be attracted. So they're lines and arrows, similar to magnetic field lines, which again, you haven't learned yet. It's part of Physics 30 as well. But these lines can tell us a whole bunch of things, right? Most importantly, the direction that the electric force would be on a positive charge. And if we have more of these lines, that means we have a stronger electric field. So the density, or how many lines we got. So if I add in all of these field lines, we now have a stronger electric field, right? It's just kind of a model of what's happening. And what a field really is, it's an area of influence around, in this case, a charged particle. And if another charged particle is placed within this object's field, we're going to produce an electric force. But every object, even by itself, if it's charged, has an electric field, right? So electric fields can exist with a single charge, whereas electric forces require two charges, right? Now, if I put a negative charge here, we're going to have an electric force directed towards it as an attractive force. But the electric field, right, is separate from this electric force. It's actually what produces an electric force when a second charge is placed there, right? And always remembering that it is reliant on a positive charge to determine the direction of those arrows. All right, the closer lines are together, the stronger the force, right? So when I drew in those other lines, we're increasing the force, at least showing that there would be an increase in force. And this is radial, right? All of these lines are radial lines going radially towards it, right? So when we're working with point charges, we're going to be producing radial fields that are always directed perpendicular, right, to our center point. All right, now we have fields around a charged metal sphere, very similar. If this is a positive sphere, right, all of the charge is going to repel to the outside. These positive charges are going to separate as far away from each other as possible, and they're going to leave the inside of the sphere electrically neutral, right, with zero electric field inside the sphere, right? As soon as another charge, positive charge, would be added here, it would try to get itself as far away from all of the other positive charges as possible on the surface. This is just kind of something you got to take as is for now. There's more information on this in Physics 30, and even more in and beyond into university, studying Gauss's law and lots of fun stuff with that. All right, but as these are positive, if we were to draw in our field lines, they need to be pointed outwards because our positive test charge, right, would be repelled from the positive sphere, and that electric force would be drawn away, right? So if we have a positive and a negative, this is what our field lines are going to look like, right? We draw in our positive test charge here. It's going to be repelled in towards the negative, right? And kind of get these cool flowing patterns, right? Going away from the positive, going towards the negative in this very unique way, right? With all of these different field lines. Too positive is a different story. If we put a positive charge here, it's going to try to repel away, but it might get stuck in between because we have another source there, right? So if it was perfectly in line, you could actually almost levitate a positive charge in between there, right? But as soon as you raise it up a little bit, it's going to get shot out away like that. If you want, you could play electric field hockey to kind of visualize that. Just Google electric field hockey. It's lots of fun. All right, now we have these charged plates, right? With this, again, this is our electric cell or our battery. So we have a positive being longer side, negative being shorter. So the one that is attached to the bigger is obviously our positive plate, and the smaller is our negative. And when we are working with these parallel plates, we use this assumption that we have a uniform field in between them. And this E is not for energy, it's for electric field. Very easy to get confused. It should actually have a vector arrow over it. That's how we need to keep them separate, because electric field is a vector quantity, whereas energy is scalar. So depending on how far apart these plates are or where we're putting our charge, let's say I put a positive charge here, right? Now we have a different distance down that it would travel, right? And the electric field strength at this point is going to be different than the electric field strength at this point, because we have a different distance that this charge would travel. So the electric field strength depends on the distance, either between the plates or between where we are zoning in on, right, where we're placing our positive charge. And it's also dependent on this voltage source, this V. And we don't know what voltage is yet, but we'll get there. So electric field strength is equal to our voltage divided by the distance between the plates. This will only be true when we're working with uniform fields, right? When we're working with parallel plates. And when you get outside of the parallel plates, you get kind of this weird bending, because right? There's no more charge pushing it down here, right? It's going to have this edge effect, we call it. Don't worry too much about this, not too important. All right, voltage or electrical potential. This is probably new for all of us. We've heard this word, but maybe we don't quite know exactly what it means. So electrical potential, kind of think about it like gravitational potential too. But we're going to break it down into this idea of work divided by charge. So electrical potential at any point is the work done per unit charge on a small positive test charge, moving from infinity to that point. So this is a very wordy example. The videos break it up in a nicer way than this. But essentially what we're doing, we're taking this little test charge and we're moving it to some point, right? We're going to take this positive guy and we're going to move it over here. In order to do that, let's say we have a large positive source here, lots of positive, and we need to move it some distance, right? Because work is force times distance. So that distance is from infinity, really far away, right? Really far distance, to this new point. I should probably put it here. So it's moving from infinity to this point in space. So we know the distance it's had to travel, and which is infinite, and we have this electric force that is required to move it there. So we'll break it down into an easier way to think about it, right? Voltage is the amount of work done, right? So we're measuring that in joules. Work and energy are both measured in joules. Work is force times distance, right? Energy is the ability to do work. And we're going to divide that work in joules by the charge in coulombs, right? So it depends if we're working with something that is 1 coulomb in charge or maybe 1,000 coulombs. We're going to have a different voltage depending on how much work it takes to move it to this new location and that charge. So there's a difference between electrical potential energy and electrical potential, right? Electrical potential energy is measured in joules, and electrical potential is what we think of as a volt. So we got to keep this idea separate. We're not working with energy, we're working with joules per coulomb or volts. So 1 volt is equal to 1 joule per coulomb. That's an important thing. Might as well write that down. 1 volt is equal to 1 joule of energy or work done on that charge per 1 coulomb. All right, this is probably the hardest thing so far in the unit. Don't worry too much where we get this from. I would just focus in on this formula and this formula. If you can remember that, you'll be good for all of our purposes here. Okay, remember this is a scalar quantity because work or energy is scalar and charge is scalar, right? We have 2 scalar quantities making up voltage, therefore voltage has to be scalar as well. So if a charge, some unknown charge Q, is moved from a position with a potential, right, potential difference between 2 points or a voltage, so the voltage of V1 to a position with V2, we're doing work, right? We're solving work from our equation where V is equal to W over Q. We're just rearranging this to solve for work, so you need to multiply V times Q. So Q is the charge of whatever we're working with in coulombs, and voltage is final minus initial. So where it ends up, whatever that potential difference is, final voltage minus initial voltage. Right? That's our change in voltage. So in order to do work, you obviously need to have a change in voltage. Otherwise, you won't be applying any force to it, and your work is equal to force times distance if force is 0. Doesn't matter how far you move it, right? Distance or work will be 0. So this is similar to, right, just thinking about pushing boxes with a force, but now we're pushing charges with an electric force. So you might come across this PD, potential difference, right? And that'll just be our volts, and it needs to have some change in voltage for it to actually produce any point of work. And just like our distance traveled, right, we are independent of path. It doesn't matter what path we take, we're going final minus initial. So the electron volt, you're gonna possibly hear come up. It's a different alternative way to measure energy, and we'll work with it a lot when we're working with smaller energies or energies focused in around electrons and electricity. So electron volt is another unit for energy, just like a substitute for joule, and you can easily convert between electron volts and joules using this value here. So it's the energy gained when an electron is accelerated by a potential difference of 1 volt, right? So the energy is equal to the ability to do work. So work is equal to voltage times charge. So 1 potential difference of 1 volt times charge of 1 electron, we get this number here, 1.6 times 10 to the negative 19. Super tiny, right? We're not going to use this when we're talking about springs or when we're talking about massive objects. We're working with really small scale things like electrons here. So the energy gained by a single electron being accelerated across 1 volt potential difference. Okay, moving on to current. Current isn't really discussed all that much. Yeah, it is. It is part of Physics 30. Not a ton of time is spent around here. We spend more time in this Physics 35, but here's kind of our intro to it. We're going to be working with it a lot more though. When a field is applied in a conductor, right, we're talking about an electric field here, that contains free electrons. The electrons drift or kind of travel in the direction of that field. And we call the movement of electrons electric current. So you need to have an electric field acting on something like a conductor, right, that contains free electrons. And the interaction between that field and these charged electrons will produce an electric force, which will move these electrons throughout that conductor, producing a current. So current is always focusing in on the movement of electrons. All right, where do these words come from? There's some good history to this, going back to the Greeks and their discovery of amber producing static electricity. I encourage you to watch this video for some history and to just catch up on our vocabulary here. And last but not least, we have this confusing idea of conventional current versus electron flow. So if you do watch that video, you'll find out that Benjamin Franklin, right, thought that we had positive charges moving through our conductor creating current. But we obviously today know that it's these free electrons that are moving. But people like to hold on to tradition, so they often will still talk about conventional current and this really backwards way of thinking of positive charges moving through where in fact we actually only have electrons, negatively charged particles, moving through. So conventional current is where this imaginary positive charge would be directed, right, where it would flow through our circuit, and electron flow is where our actual real electron is flowing. And they will always be opposite because positive will flow away from the positive battery node, and negative will always flow away from the negative. So conventional current, you'll hear come up, it's kind of the backwards current, but think about conventional being positive, and electron flow being negative. In physics 30, we only work with electron flow because it's the real one, the more intuitive one. But IB does occasionally work with conventional current, so be aware of that difference there. All right, I'm gonna stop the video here. We'll get into electron drift after Easter. Enjoy the break, everyone. Hopefully this wasn't way too much overload. Don't panic too much. What we're doing in Physics 35 is built off of what you haven't learned yet in Physics 30 and what we just reviewed here, but we'll get to it later. See you.